Thanks for coming to the RIST Forum. My name is Kieran Kunhya. Apologies for my voice. I've tried as many Strepsils and off-brand Dutch equivalents, but it doesn't seem to help. So I'll be a bit quiet and muffled, but never mind. If you want to email me, it's there. So who are we? What does our company do in open broadcast systems? We make encoders and decoders for contribution, B2B broadcasting. I still need to make that point often, but I guess most of you are here, you probably know the difference. What's different is it's based around commodity off-the-shelf hardware, so you can buy these parts almost anywhere in the world. And our general sort of target areas are news, sports, and linear channels. And because we're based off COTS hardware, we are transport platform neutral, so we actually, this is the first platform we've officially supported, but we've supported many of the other market variants for many years. The vast majority of our work is open source. We have a Red Hat style business model. I guess, just to put into context, what you'll see, we have quite iterative design approaches. We're vertically integrated, so we do everything ourselves, so we can move quite quickly with implementing things like RIST. So where did we start with all of this? We've had FEC running for a number of years, even on quite poor public internet circuits across a wide customer base. And I would say, broadly speaking, this was good enough to be used, I'd say, within Europe. There were many others who used them for things much worse than, say, quite well-connected European ISPs. And so in version 1.4, we added something called dual streaming, so being able to send the same feed over multiple paths and also time delayed on the same path. And this was really the first attempt to try and do something quite extreme to recover packets. And later on in 1.4, we added ARQ, for those who aren't aware, automatic repeat requests, and this was based off RFC 4585, well-known standard. That, as I'll say in a bit, it ended up becoming quite similar to RIST. So what are the real problems? The biggest problem we have is FEC can't cope with large burst losses. I'll talk about that in a minute. Has quite limited interoperability. I don't know if anybody here has actually implemented FEC, but it's actually pretty complex. It looks simple, but actually the subtleties of implementing the matrices that could have infinite iterations are pretty complicated. We had end users who did dual streaming, so sending the same feed multiple times down a path, and this had quite a heavy bandwidth penalty. Sometimes the bandwidth penalty was comical. Sending 6 copies of the same stream to the receiver over multiple links. So in some cases, even more than 10, hundreds of megabits just to receive a 20 megabit feed. But that's what we did at the time, and to be fair, it was low latency. And I guess with regards to some of the proprietary protocols, we have a customer base unwilling to pay per gigabyte for this. In the old days when it was being compared to satellite, the costs were kind of reasonable, but now it's IP compared to IP. Where the transport protocol costs a lot more than the connectivity, that causes a lot of issues. And I think a wide part of our customer base was clearly unwilling to do that. Yeah. So just to kind of labor on this point a bit, FEC is based around matrices. If you have bursts that's larger than the matrix size, which is often the case on the public internet, you have problems. Interoperability is pretty bad. Some equipment wants block aligned, some wants non-block aligned types of it. Also, the latency measurements in the spec, they're just wrong. I've told them, they don't seem to care. Yeah, so it has many problems, but it's still used. So where we were this time last year, before RIST was published, we were using FEC on the public internet, and we still do across Europe. It's regularly used. And we had our own internal ARQ used across private lease lines that happened to be a bit lossy. And RIST was published in October 2018, and it was a relatively straightforward change. I think there were some subtleties. You signaled losses in you signaled retransmissions in a slightly different way to we did. So it was a relatively small change. You could probably even see it. So this is upstream to the UPipe project, upipe.org. The changes are very small, and so I was quite pleased that RIST ended up being how we originally did it. And obviously, we did it correctly, so if it's very similar, it must be good. So the biggest question ever in the world so far is why did we not incorporate SRT? SRT was released in April 2017 at NAB. It's built on quite a complex code base, but to be fair, they've done an incredibly good job making it a very, very simple for end users to integrate, possibly to the stage that end users can integrate it without even knowing what it is. It's built on a file transfer protocol, UDT. Also has some kind of strange design decisions that were possibly not driven by MPEG-TS, but were driven around file transfer. Most manufacturers use a PCO in their transport stream. We've been using it for nearly 30 years, but they seem to have reinvented it. But it did a lot of really important things. It did drive the market towards an understanding of protocols that are for delivery to end users, HLS, Dash, et cetera, compared to an understanding of B2B protocols for contribution, usually transport stream based. And what was even more impressive was last year they actually released a specification that was 89 pages long, and someone must have really sat there down and worked really hard to document all the idiosyncrasies of UDT. This is actually quite impressive, to be honest. This goes on because this is a question we're asked a lot, and I want to use these slides in the future. And so I want to answer this once and for all. Technical debt. I use the phrase a lot, but this is kind of important. This is really the biggest problem. Technical debt, and in our company, this is really, really important to reduce technical debt as much as possible. They've gone for a decision to make a file transfer, to modify a file transfer protocol and use it for live, rightly or wrongly at the time. But that's the debt that they borrowed. And 20 years later or 10 years later, they have to pay that debt back in the features they can't implement easily, bonding, etc. So it's very complex to add new features. It's a very complex code base. It's heavily burdened by massive technical debt. It's very difficult to debug SRT issues, and I'll talk to you about why RIST is very easy to debug in a minute. For us and for our customer base, probably the key thing was RIST had multi-network and multi-point support from day one. That was a key requirement. In SRT, that wasn't possible. So SRT is widely supported and in the main works. It's difficult to add new features, however. It's pretty complex. So my personal opinion will be SRT will be the prosumer solution, RIST for the professional users. Comparable, say, to RTMP for streaming and a transport stream to professional workflows. So why is RIST good? It has a very large heritage from IETF. Someone came to my booth who'd worked on this and said, hey, we did this 20 years ago. And they're right. Retransmissions, they're not new. And this is a technology used by really billions of people. You make a FaceTime call, you make a WhatsApp call, you make a WebRTC call. It's doing retransmissions. They work. And a relatively simple code base, a relatively simple protocol. So similar concept. I've already covered this. Prosumer versus professional. The lack of technical debt in IETF RTP standards makes it future-proof. There's a reason we still use these standards from 20 years ago, RTP, RTCP, in applications like WhatsApp and FaceTime. That's really important. They're very simple. They're easy to build on. So yeah, let's go. Let's deploy this stuff. Iterative design, as I mentioned. You can use as many network emulators as you want, but nothing beats reality, as a number of the people in the room know and saw. So we had our first beta, I think, toward the beginning of the year. Deployed as a backup on a few sites. I think within a week or so, we had customer responses going, hey, this is what I think, fed back. Some of the sites were really interesting, in the Middle East in particular, where the data suggests the operator's doing something a bit unusual. They have some kind of weird traffic shaping going on. But the first key feature we implemented was retransmission on both links. In the beginning, we were retransmitting only on one link. And then these changes were deployed to production, and now they contribute feeds of pretty millions of people watch pretty much every day. And I think I can cover the map. Is there a map? Yeah, so we've deployed RIST so far to all these sites. Most of these sites, I think, have 2 ISPs. Some of them have 1 for a wide variety of applications. Really important to have 24/7 linear channels. This is often for, to be quite honest, quite low-end playout, simple playout to a satellite uplink. This is one of the most expensive costs often for a broadcaster. They spent huge sums on satellite capacity, and they haven't got much left to get it there, to get it to the uplink station. Interactive two-way talking heads for news. This is really important in Britain at the moment, for example. We have lots of politicians disagreeing with each other. Live events, especially, actually a couple of days ago in particular, but just live events, turning up at an outside broadcast, using a lease line, sometimes the public internet, doing a live event at quite high bit rates, 45, 50 megabits, 10-bit 422, Dolby E, you name it. Also long-form studio programming from different parts of the world. These were the primary paths to the air. And also reverse vision, so allowing reporters in the field at bureaus or in different locations to see content for monitoring purposes. Really useful. All these different applications that we've deployed RIST for. Operational comments. So lots of products at IBC make the claim that IP is plug and play. Various different cloud products, etc., etc. You will always still need an IP engineer of some sort. And what's really, really useful operationally is being able to run TCP dump or Wireshark. I've got existing RTCP dissectors, again for other industries, and this is an actual capture. You can see retransmissions, you can see other things. With other protocols, proprietary ones, other open source protocols, this isn't easily possible. Now what? We've done quite a bit of RIST. I'm asked about main profile a lot. To be honest, for us, not that interesting. Most of the time we need a control plane of some sort, and that that should go over a VPN. Emphasis on should, unfortunately. And since you have an encrypted way of controlling the remote device, the RIST makes it possible to use that VPN capability to actually transfer the video. Some big caveats: some VPNs are not really designed to transfer tens of megabits of video, so be careful. Other useful thing, somewhat RIST related, as a result of using that VPN, you can now do one-touch provisioning of encoders and decoders. You can post equipment, you can ship equipment to anywhere in the world. People can plug it in. They don't even know what it is. They just think it's a tunnel. Although I did say IP engineers are not needed, you can do things like phone home on port 443. That will work. Or now, because now 443 on TCP for SSL and 443 for UDP is now used a lot with encrypted traffic in Chrome, for example. So the main profile isn't that interesting for us in the long run. But there's one big key thing that we want to do with RIST, and that's use this thing called the cloud. There's huge potential for the cloud in live workflows, and this is not just in OTT. So there's a lot of use in cloud for OTT, but relatively small amounts of it in traditional broadcast. And so I wanted to show an example of some of the things you can do in the cloud. And one of our partners at Google Cloud Next in 2018 actually ran significant chunks of the broadcast in the cloud. As a broadcast service, I'd emphasize, not just hitting a post-produced, for want of a better word, stream into the cloud, then transcoding it into ABR, etc. They actually produced live feeds from different parts of Google venues in the cloud. They rendered multi-views in the cloud, fed them back as transport streams. They didn't use RIST, but it is technically possible for them to use that. They stored all live feeds in the cloud. They had edits in the cloud backed on, at the time, Google Drive. And that was really made possible by a retransmission protocol that led to these things. The retransmission protocol is the only way you're able to render multi-views in the cloud and not have them glitch all the time. Have the feeds going in and have confidence monitoring, because if the streams aren't confidently going in anyway, to begin with, you can't monitor them. And we hope to see that more broadcasters use literally spin up and spin down workflows like this, as it's really, really powerful. It's a lot of rigging, a lot of infrastructure that doesn't need to be there anymore. And it was really useful to be able to do that at a cloud event to prove its point. So all of the multi-views you see there, rendered in the cloud, all incoming feeds as transport streams, that transport stream being fed back. So the end. We've deployed RIST, dozens of global locations for a wide variety of broadcast services. Today, it gives us what we need, the capability to do vendor-independent retransmissions. That's really useful. But really, the future is using the cloud to spin up and spin down broadcast services. That's why it was really great to see AWS endorse RIST. That's really useful. I believe it's in Media Connect now. That's really great. And we hope to see more of it. If you want to see RIST in action and find us at hall7.a49. Thanks. Questions?
You say that you don't see much use for RIST main profile, right? Let's explore that a little bit. There's tunneling, there's encryption. None of that's necessary in your environment.
Again, so as I said, to control the device in remote locations, you need some kind of VPN that's already there to be in our environment. That VPN can do things like tunneling 443, can do weird, what's it called? NAT port traversal in various shapes or forms and various guises, and it has inbuilt encryption. So for our use case, we don't need to encrypt. It, in our opinion, it's a problem solved at a different level. And it means the customer can choose what type of encryption they want, different vendors as a whole. VPNs are a solved problem.
So you're using simple profile over a off-the-shelf VPN. Is that what you're doing?
Yep, software or hardware. Sometimes if it's software, it can run on the device. But we have customers that, for various networking IT reasons, use various commercial VPNs available in the marketplace.
Which VPN?
FortiGate, OpenVPN, Tink, you name it.
Okay, thank you.
No more questions? Okay. Oh. Was that a wait? Was that a head scratch or a question? No. Okay. There's always one. I have to pick them out. You have to pick them out. All right. Cheers. Thanks.